Right, so my name's John Harris. I'm currently a technical director, but from September I will become the Director of Research and Innovation at HR Wallingford. My primary sort of research interest area is actually marine scar and scar protection. What I'm going to sort of do in this presentation is provide a sort of very good overview of some of the work we've been doing over the last sort of 5-6 years, looking at data from built projects, and to demonstrate how important actually using data is to enabling our own understanding of scar processes. Just as an aside, I thought I'd ask the audience, i.e. you, what do you see in this picture? But no, there's no trick question. It's sort of, you can just well, actually, it's Anthony Gormley, but sort of a statue of Anthony Gormley. But my answer is that, I mean, that's what it's a fine answer, but my answer is this is a research opportunity. So
it's nice calves.
So one of the why I think sort of the natural environment is a classroom, because it challenges our understanding. So when we get data from the sort of built environment, often it doesn't agree with what, well, we hope it does agree with our theoretical and empirical models, but sometimes it doesn't. And therefore it teaches us important lessons about the physical processes that we're trying to reproduce. It provides us with a research opportunity. So here, this is actually Crosby Sands off in Liverpool Bay. I think there's about 100 Anthony Gormleys sort of stacked along the foreshore at different locations. So theoretically, if you wanted to monitor every statue, you could look at the variation in shore levels along the whole foreshore. So again, that's why I sort of, that could be a research opportunity. The other thing about looking at data from built projects is that it's at full scale. So there aren't any scale effects, unless you've got my bad sense of humor, unless you're looking at fish. So, so what I'm going to show you, so here, this is what I call an opportunity. So here we have 2 digital terrain models built from multi-beam images. They're both at the same. So this is a offshore monopile for an offshore wind farm. And the 2 images are about 8 months apart. So if you were to look at those 2 images, you'd say, well, the scar development around that monopile is actually, it looks fairly stable. So going back, so we've got 2 digital terrain models, same monopile, about 8 months apart. Roughly, you'd say, just as a quick look, you'd say the scar hole's fairly uniform sort of between the 2 images, therefore there's not been much going on. So here we have the same monopile. This is probably about 3 months after the first image was taken on the previous slide. So these are time slices. There's more detail if you want to, the work's been published, so if you want more details later, you can find the paper. But if you start to look towards the top right of the scar hole, you'll start to see deformation of the soil layer there. So gradually, over time, so this is happening, the overall effect will happen over a 75-minute period. You can start to see that feature developing, and then finally, those are the final sort of images from the Scour hole collapse. Well, this is a geotechnical process and not a Scour process, but it's something that from a sort of hydraulic engineering point of view, we were unaware of. So if we were to model this in a physical model, we would not be able to reproduce this effect. I mean, we've done numerous tests in physical models and have never generated this Scour collapse. Just to give you an idea of the amount of material moving, it's about 450, 500 cubic meters, which is equivalent to probably about 8 40-foot containers, sort of shipping containers, or about 17 20-foot shipping containers, depending on what size you like to play with. That's a lot of material. So moving. Now, in this instance, the cables coming from the turbine are actually roughly running along the flow slide length. But if one of the cables was cutting across that, then potentially that's a lot of load on a cable and may actually provide you with a mechanism for failing that cable. One of the advantages so we were lucky in doing this. So we had a workboat on site at the time, and it just happened to capture this, and it kept going back and forth. Otherwise, we'd be unaware of this. We think it's so within the paper we did a forensic analysis. You never have all the data that you want because this is from a field study. So we have the multi-beam images. We have a wave buoy on site. There was a current meter on site. Unfortunately, the data from it was rubbish because it was having error on it. We actually used a numerical model to predict the tide and the current at this location to make up for the lack of current data. But we didn't have a lot in terms of the geotechnical soil properties. We knew what the soil properties were from when the monopile was installed, but that was about it. So we had to sort of try and create a forensic analysis of the whole process to try and work out what we thought was going on and why it had happened. In the end, we concluded that in Scour holes, because this is a tidal location, you've got the sort of spring deep cycle. This failure occurs at the top of the springs. We think the Scour hole is gradually getting steeper and steeper and steeper until you get to the peak spring event, and then it relaxes, and you get a sort of pore pressure response at the toe of the Scour hole sort of results. It's almost like we've seen something similar. The Dutch have done trials with dredging where they sort of use a suction dredger to sort of collapse slopes. And we think the process with the wake vortices and the horseshoe vortices, lifting material, creating a negative pressure, we think that's the sort of mechanism that's happening here. But there may be other alternative solutions, but that was our sort of best guess on why this was forming. And we've seen this occur at other sites as well, so we know it's not just a sort of one-off at this location. So that's something that we would never have known about if we hadn't captured it. So just quickly, I've just done some cross sections so you can get a feel for how the slope evolves. So you get to the final slope collapse. So you've got significant infilling of the Scour hole, and then 8 months later, the Scour hole is almost back to how it was before the collapse happened. The only thing that's slightly different is now the Scour hole is slightly wider at the top and a fraction deeper at the bottom. So these sorts of events may provide a mechanism for increasing the extent of these scar features and possibly making them slightly deeper as well. We have expanding evidence database from the field as more and more projects are being built offshore. Here we see two very sandy environments, sand waves, monopiles in both cases. And here we have two environments which are much more cohesive. We have a bark and dune over a sort of boulder hill, and then we've just got a sort of monopile and boulder till, and you can still see the spud can depressions from installation as well as the cabling scars from jetting. One of the areas that I've been extremely interested in the probably last 10 years is scar development in non-uniform soils, which for us, I mean, Fraser will probably kill me for using cohesive soils, but as a hydraulic engineer, we've been trying to sort of better understand how we can reproduce scarring in these more complex soil environments. One of the methods we looked at very early on was some work done by George Annandale, where he proposed what he called this erodibility index method, which is based on stream power and a number of factors. In addition to that, there is another method called Shrikos, which was proposed by Jean-Louis Briot. But again, this is, but it doesn't take into account anything about the soil properties, but may provide you with a maximum scar depth in these sorts of soils. The advantage of the Annandale method is that you can bring in field information from the geotechnical studies, such as undrained shear strength, which is potentially an advantage when you're trying to sort of model these soils, because that's the sort of information you'd get from a geotechnical survey offshore. However, because we have a lot of data coming back from the offshore environment, we can sort of model what we would predict compared with what we actually see in the field. And as you can see from this sort of sample of data that we've looked at, in some instances it's not doing a bad job, but in most of the instances you'd say it's actually under predicting. So actually, so this is based on George Annandale's methodology. So actually the model is unconservative in most instances, which as a designer is an issue. So we collected sort of both. We used all the data we could find from laboratory tests, and then we also collected all the data that we had from offshore sites, and we plotted a dimension of scar depth. So here we've got scar depth divided by the pile diameter, and along the top we've got undrained shear strength. And we plotted the data, and then we fitted an envelope curve to it. There's a number of points which lie out of it. Most of these points relate to bridge scar data from the US, and we think that they don't fit within the envelope because they're dry riverbed, and there may be a different process happening in those instances. There is one data point from an offshore location which sits below the curve, but we don't have access to the full data set, so we don't quite know whether that's a analysis error or so we've left that. But in general, the curve fits quite well. So our reading from this is that as you get into stiffer, stronger soils, using undrained shear strength as a proxy for scar depth isn't a bad fit. However, in these very weak soils, you can almost think of a number and that's your scar depth. And we think in these very weak soils, there's the sort of the properties of the soil. There's more elements of the soil which have an impact on how it evolves. So if we go back, so one of the things, so looking back at the Scour depth, clearly from the Annandale predictions we were looking at, we know that the Annandale method has been calibrated for bridge pier Scour, and so what it's lacking is, so either the method is wrong or we're missing something. Because these are all monopiles, the offshore data is for all monopiles offshore. One of the processes that the Scour formula do not take into account is cyclic motion of the piles. And so if we look at the cyclic deflection of the piles relative to a dimensionless Scour depth, we can see that actually there is a relationship between the deflection and scarring in these soils. So what we think is happening is, in the same way, if you have a fence post in your garden and you wobble it, you get gapping mechanism and you get high pressure flows which actually mechanically break up the soil. So not only do you have shearing creating potential scar around the monopile, but you have this mechanical motion, and therefore when I did the original work, which is these open data points, I was thinking, okay, scatter, but they all fit on one curve. So I've got my dimensional parameters correct. However, before I came here, I got the data set. Whilst it still continues the trend, it doesn't, it's below it. So clearly in my non-dimensionalization of this problem, we're missing a function. Now it could be like rotor diameter, speed of rotation. I don't know, but I something I need to look at, or if someone is interested in taking this problem forward, then I'm quite happy to share data. But it's interesting. But what we haven't done yet is make this mechanism back to an additional formula for Scour development. So we rely quite heavily on using this curve to as a proxy for telling us what's going on. The issue comes when we have very weak soils. So my final slide is really a hybrid solution. So we did some work relatively recently in the Baltic, where the soils were very weak. So there were sort of Holocene, sort of silt clays, with an undrained shear strength of the order of 0 to 15. The client wanted to see whether possible to install the monopiles without installing scar protection. So one of the things so initially we did a prediction using Annandale's method because we could use the CPT information that was collected at all the turbine sites. But we know that George Annandale's method is unconservative. So we recommended to the client that we do soil sample testing. So this is something that you guys do a lot of here. So we have a sort of crude erosion rig we created, and effectively you can sample core it and wind it up and erode it. So, but we need to be selective. So one of the issues with offshore wind farms is that there's a lot of foundation. So we had to be very clever in terms of what soil samples we picked across the site. So what we tried to do was pick soil samples that would be representative of the site as a whole. And we tested those in our erosion rig. And we got a set of values of rate of erosion for the different samples. We then took the top 10 samples and then the average of the lowest group of samples and created a cumulative curve, which effectively is a probabilistic approach, albeit that we're doing it in centiles. So saying that use this, then 50% values will be below this value. So the reason why we averaged the lower values was because for some of the samples they didn't erode, and also for some of the weaker samples they were weak because they were just small lenses, pockets of looser material in the samples that we eroded. So we didn't want to over bias the curve. We then used the rates that we got from the testing to go back and modify the Annandale bits. And here you see one example. So the dots are the erosion tests, and the line is what we've got from the CPT testing. And then we went on and we used that to repredict the scar development. The monopiles here this is just a selection of the representative sample of the monopiles. So here is an example of where you're using field information, you're using lab information, and you're using empirical information to help you predict what's going on at a site. And I think for me, as a sort of engineer, that's the future, is using the combination of field, empirical theoretical understanding, and lab to actually come up with a good engineering solution. And with that, I will leave my talk. There's more details in the papers, and I'm happy to talk to anyone later. It was a very rapid go through, but I think the point is that data is important, field data is important.
We'll open up for any questions briefly. So Fraser's got your hand up first already. Yeah.
A question about the evolution of the. Yeah, sure. My question's about how the scour around a monopile evolves, and we're seeing rock boom diameters that are 4 to 5D, but the graphs that you put up there looks like most of the scour is happening actually at the monopile.
Yeah.
And I'm just interested on your thoughts on why we're ending up at 5D when all the scours looks like it's quite localized. But
for the monopiles, it's the principal driving mechanism is the downflow down the face of the pile, and that sort of then generates your horseshoe vortex at the face of the pile, and then you get the flow separation around the back, and you get these wake vortices, which are effectively like a vacuum cleaner sucking up material at the back of the pile. For other structures, then it can become slightly more complicated. But the other thing to point out with monopiles, and certainly in the tidal case, so we tend to think that the slope, the extents of a scar hole are dependent on the angular repose of the bed material. So that tends to relax over time. So you'd probably get slope angles about 15 degrees sort of in both directions, albeit there may be some asymmetry depending on the tidal asymmetry. On other structures, so you can get, for something like a gravity-based structure, you can get the flow, the scar can form away from the structure. So it starts to be pushed out. And we've seen that we did some experiments in the lab where we did different shaped gravity-based structures, and instead of the scar forming at the front of the structure, the flow separation pushes it out, and then it started sort of almost to the sides of the structure. So it would be good to sort of look at the sort of the flow conditions around the structures that you're looking at to see what flow mechanisms are taking place and where the changes in the bed shear stress are happening. That might be why you're seeing a sort of different evolution of scarring.
Can you just show the previous slide? Because I thought it was very interesting. Thanks. Ooh. Okay, I agree. You've sort of done best practice here. You've got element tests, you've got field data, you've got a real site. But if you actually look at the predictions of the high estimate to low estimate, you're ranging from about 0.2 meters to about 5.5 meters. So a factor of 20.
Yeah.
I get complained at if I give uncertainty ranges that wide for geotechnical things, which I agree are equally uncertain. Is that just saying we don't know, or is that saying, can we get that better is the question, or is it intrinsically an uncertain process which we have to live with?
I think there will always be an element of
There will be uncertainty.
uncertainty.
Yeah.
However, I think we can do better. I think based on what we have currently, this is as good as we can get. We based our, so for design purposes, we based on the median value, and I suppose in terms of the client themselves, we have put in place mitigation, a monitoring process which allows them to monitor the situation over time, and therefore, should things vary from what we expect, they can then undertake remedial work. However, they were happy with what we did and with the fact that yes, there is uncertainty, but there was enough, I suppose, understanding of the process to go, okay, we're happy, we can live with that.
Yeah, I mean, I think it's all about context and whether you've got time to react. So otherwise, we'd have to design. Let's say we're geotechnology giving that information. Do we have to design assuming a scour hole of 5.5 meters for all our foundations, make all our foundations longer, or can we live with it and react, as you say, and look out for it, knowing that it's happened? It's very interesting, holistic design.
And I think for our point of view, we're seeing a lot more clients now saying, do we have to install scar protection? Because it's expensive. So we're doing a lot more of the analysis in terms of trying to limit what we think the scar development will be over time. And these are based on cohesive soils, but we've seen it in deeper sites where actually the scar evolution is not limited necessarily by the soil conditions, but is limited by the duration of the events that you have. So actually, if you run a time evolution for scar at the site based on hindcast data, the scar development at the structures cannot achieve the big scar depth because the events don't last long enough, and therefore that limits the scar development.
Around monopiles is, 10, 15 meters sometimes out from the monopile, but it looks like all the scours happening 1 meter from the monopile. So why is the scour protection being applied so far from the monopile? And can we live with a failure driven by the vortices that are being shed 5 meters away? But
so for a monopile, normally you'd assume for most rock protection installed offshore for monopiles, you assume an amplification factor around the structure of about 1 diameter. It may be between 1 and 1.5 diameters, but then the scar will then, you can then limit the scar protection from that point. So typically a sort of top width of a scar protection would be about 3.5 pile diameters. You can see bigger scar holes if you allow the scar to form. I mean, some of those structures are over 120 meters from side to side, so they are big features. But in terms of the scar protection itself, you can limit it, albeit that you need to be aware of the other conditions that exist at that site, such as general seabed changes due to sort of sound waves, general sort of mobility, So we have done work, say, in Taiwan, where on one of the sites we looked at, they had sand wave heights of up to 17 meters. And we were being asked to look at scar protection for a site where potentially the bed level could vary by those sorts of distances. So that suddenly becomes problematic from a designer's point of view as to how you protect foundations, those sorts of changes.
Right, wrap up so we can move on to that. So thanks, John. Everyone, thanks, John, again. Not sure. I was late coming down as well, so I hope, did someone give you an introduction, John, at the start? It's good. So, anyway, John is a key partner for us. So he's been here for a few weeks now, heading off, I think, or heading away from here in some time with family the next little while. But with Wallingford being a key partner in Tide, we've even the last few weeks had discussions about ways to maybe expand on the research, sitting in a lot of meetings with the team. So I think at the end of the day, Wallingford is recognised as one of the, not just the UK's, but the world's premier groups for dealing with Scour in the marine environment. So we were lucky to have them as a partner. So thanks, John. So we'll move on to our second speaker. So Connor's going to come up. So Connor Duffin is back for the defence of his PhD. I think next week is his Viva. So Connor, I think you did your honours degree here in 18, at the end of 18, something, and then joined the Offshore Hub, Project 5, working with Ed and Melinda, and also Mark Girolami from the Turing Institute in the UK, and impressed sufficiently that was offered a postdoc position a year before finishing his PhD and buggered off on us. Went over to the UK and has finished his PhD now. But we're lucky enough as well that, today he'll talk about his PhD work and what he'll defend next week. But we're lucky enough also through the connections with the Turing to have Connor continue to work with us for the next few years on Tide, and we're really looking forward to that. So hopefully you're over the jet lag and you're ready to go. And please, floor's yours.
Thanks for having me. Yeah, I started my PhD in 2019 now. I'm a research assistant, as Phil said, at Cambridge at the moment, whilst concurrently for about another week, PhD here at UWA. So the main reference for this work is this paper, which was published in 2021 with Ed Thomas, who I think is going to have a Tide affiliation soon, and then Mark Girolami, who's now my boss. So the motivation for this work was that Ed and Matt Rayson had looked at this internal wave model way before I started my PhD, and had thought about ways to synthesize it with an observation, with a set of observations taken across. I'm going to call this data set Y, which is indexed by this N here, which just means the whole set of data up to the time point N. And the KDV equation is quite famous in the PDE's literature because it's integrable and so on. But it has three parameters that that sort of characterize its behavior. I'm going to call these collectively as capital lambda. We wanted to find a way to try and use this set of data to correct for some instance of model misspecification. So your PDE itself is not actually representing, when you solve it numerically or analytically, what the physics that you're actually observing is. One way to try and correct for this model misspecification is to posit that the parameters themselves are just not set correctly, and we need to change those parameters. We took a different approach, and we were going to say, because this is such a well-studied problem, this is the inversion problem, if you've heard of it. If we instead conditioned on a fixed set of parameters and just said that we have a good idea of what they are and what they should be, because physicists have looked at this stuff for a long time, how we actually want to construct not the measure where you're conditioning on the data, but what if you instead look at the solution of the PDE? So I'm going to call this U n, meaning it's the solution of the PDE at a time point n. Condition on all the data up to that time point, and also condition on the parameters that you're assuming. The work that I've done throughout my PhD is on a particular way of doing this called the statistical finite element method, and I'm going to try and explain the core concepts behind that today in about 15 minutes or so. To do so, what we're going to use is essentially admit that the model is perhaps misspecified. So on the previous slide, what we said was that this right-hand side of the PDE was 0. We're going to still assume that it has a mean of 0, but we're going to also assume that it's uncertain, and we're going to model that uncertainty with a Gaussian process, which is, I know some people here are familiar with them, but it's just a way that you can model a mathematical function with some notion of uncertainty. So it has a mean behavior, which we assume is the same as previous, but it also has some sort of temporal error structure, which is just white noise essentially, plus some sort of spatial error structure. And this says, it sort of posits that a priori we have a good idea of what the physics is, but we still have a bit of uncertainty into any additional terms that should have been included in it. This is a very nice mathematical object and so on. Perhaps you can study this analytically. We're not sure on that, but I think you should be able to. But in practice, to do this, we need to do some sort of numerical thing so we can actually realize it on the computer. We use finite element methods for the spatial discretization. So this converts an infinite dimensional problem into a tractable one. And then we use some time discretization scheme, and we get what is essentially a state space model over our representation of this PDE. And this is a Markovian process, and we have some sort of error structure. Okay. And it says this is sort of our representation of what we assume physically is happening. So it's modeled by this PDE with some admission of error, which comes in because of this error term here. So we're also going to assume at the same time, and this sort of links into what John was talking about in his previous talk, in that we're going to combine this with a set of observed data. So we're doing a thing where we're combining a known physical law, essentially, which is our dynamical process, with a set of observed data at every single time point that we're solving the PDE. The data is observed by some sort of observation operator. This observation operator is basically interpolating the PDE at a set of individual observation locations. And we have some additive noise model. The additive noise model can be basically whatever you want it to be. If you assume that there's some structured noise in your PDE, you can incorporate that not in your PDE, in your observation process. You can incorporate that into this, but we're just assuming white noise for the purpose of this talk. So that it sort of gives us a general model that maps forward with a dynamical model, and then also at the same time incorporates information from data. So it's this balance of incorporating dynamical information, which we know should exist, plus some information from the data set. To compute we take a Bayesian approach. To compute our Bayesian posterior, we use the extended Kalman filter. It's a classical nonlinear filtering method. I'll talk about some extensions later on in the talk, but if you're targeting this thing here, some filtering distribution, some sort of filtering algorithm should be okay. So I'm just going to talk about some case studies that we looked at. The first one, and perhaps, not perhaps the most interesting, but definitely the first example that we looked at with experimental data was looking at this model that I've talked about previously, where we observe 3 locations of the object that this PDE is solving for. So the PDE is solving for internal wave heights within this essentially what is an acrylic box about 6 meters long and about 30 centimeters high. And we observed the wave heights at these 3 locations. So at 3 points in the domain, we collected, not we, I shouldn't say that at all. People 20 years before me collected this data and I just used it. They collected these measurements at these 3 locations, and we wanted to see if we could synthesize that with this PDE that we had posited, as I say, a priori. What we did, so I'll give you a bit of a flavor of what the data set looks like and what the model is doing before I get into what we did. So the data set at the 3 locations looks like this. So in purple, you see the data set, and in blue, you can see what the model is trying to do or what the model is going to do. So you can see that the model is generally capturing some of these features okay, but it's a bit fast. It's sort of things happening in the model before they're actually happening in the physical system. So there's some sort of misspecification going on. Perhaps it's in the viscosity. Perhaps there's, I don't know, perhaps there's like a slowdown advection process or something going on, but in any case, the model is not specified correctly. What we wanted to do was try and combine these 2 things together to see if we can get something that fits better, essentially. And to get a feel, this is the expected value, so the mean of the filtering distribution conditioned on the parameters, on a set of parameters. Okay? And it's sort of, and you can, the posterior mean sort of does what it expects. Like it bounces around here. You can see some sort of soliton steepening events happening here, and it's reflecting through the domain. So it's sort of doing on average what you want it to do. And then when you actually look at what it looks like across the time series, you see that it fits quite a bit better than what the model was doing before. You can see that it's more or less capturing the dynamics as was posited, as you're observing at the individual wave gauges, because in it, what you're essentially doing is just pushing the model onto this observed data set and then rerunning the model from there. But quite a cool output that we get from this posterior distribution down here is that we can interpolate the wave profile inside the tank at the individual time points. So instead of having 3 data points, which you really aren't sure what's happening between them, you know, for those of you who are familiar with Gaussian process regression, you would imagine trying to interpolate these 3 things here and getting curves like this might be a bit beyond the pale. So because we're able to incorporate this physical information, we're able to do somewhat of a physics-constrained Gaussian process regression inside the domain by incorporating our a priori knowledge. I think I would imagine that getting fits like this with a GP that accord really well with your physics would be super hard. So I think that's the real strength of our method, is this sort of constraining that we're able to do. So the next example I'm going to talk about is quite a more significant, has quite a significant degree of nonlinearity, much more so than the KDV example, which is Kuromoto-Sivashinsky. So it's this rather horrific 4th order PDE that has spatiotemporal chaos. So as you vary this parameter here, it transitions to chaos with all sorts of strange behavior going on. We tried to look at an example where we generated data from a KS equation where we set this to 0.95. Whereas in our actual filtering and the model that we're using, our StatFEM model, we set nu equal to 1. So we're misspecifying the model by changing one of the PDE coefficients. And you see, I'll just skip ahead, but you see there's a rather drastic change in the dynamics that you observe when you change this parameter by 0.05. So even though it may look like it's not that much of a change, because of the chaotic nature of the system, this is a rather drastic change in the dynamics. You can see that some features are retained, like this central feature through here, but in general, it's not the case. So again, I'm going to show some plots to compare the data with our prior and our posterior. So the prior is the model prediction. You can see it's okay at the start, but then as it transitions later on into this very different dynamical regime, you see it sort of becoming much more misspecified around here. But here it's okay, but you can see, again, there's features that aren't really captured in this model. When you condition on the data and compute the posterior, the expected value of the posterior seems to match the data quite well and give a reasonable fit. You can't see the uncertainty bands in here, but they are present in this figure. To give it somewhat of a more rigorous quantification than the I norm, it looks like here, you know, if you compute the relative errors between the prior and the posterior, prior looks like it's sort of okay at the start. So for about time scales of order 5, it's performing okay. But then as soon as you get into this regime where they just shoot apart, you know, maybe about here, they just don't accord with each other and you get these huge jumps in the errors, the relative errors, that is. The posterior itself seems to correct for this and the errors sit at around on the order of 1%, 2%, something like that. And for a more visual check, you can see the expected value of the prior and the posterior seem to be shifted quite drastically. So it's pushed over more into the regime of what the data is actually telling it that that's actually going on. Sort of the current work that we've done more recently is looking into how to scale this methodology. So all the examples we looked in the first paper that I introduced in 2021, they were nice sort of clean 1D examples that weren't really of any high dimensionality. So the next thing we looked at is how we can scale it. I'm not going to go through any extra examples here for time constraints. But what we did, we looked at these systems called reaction diffusion systems, which have some generally interesting dynamical behavior. You have a dissipation term here plus some reaction term. And these PDEs model the balance of diffusive processes inside, for example, chemical reactions and the reactions themselves causing nonlinear interactions between chemical components, whatever. And when we do an FEM discretization of these systems, we get a really high dimensional state space on the order of 10 to the 4 degrees of freedom up to 10 to the 6 if you need a really high spatial resolution on these sorts of models. We compute our posterior using what we propose as a low-rank extended Kalman filter, which essentially builds upon the ideas we were looking at before and using an extended Kalman filter. But what we do instead is represent our covariance matrix via a principal components type decomposition and take the leading, I've called this K modes. So we look at the leading areas in which our solutions are varying and keep those. And apart from that, we just ditch everything else. And because of the rapid decay of the spectrum, this seems to give reasonable results. I don't want to go too much into the details because that's sort of a second talk in itself. But this is all found in this paper, which was published online in May and is now available this month in JCP. So just some quick conclusions to tie everything off. So today I talked about a statistical finite element method for nonlinear time-dependent PDEs. I showed it on some specific case examples of 1D and told you that it's okay for 2D problems. But this is a generic framework that you could use for nonlinear time-dependent partial differential equations and sort of forms the basis for digital twins type methodologies where you want to systematically and sequentially update models of some physical phenomena given a data set that's coming in, streaming in time. We leverage the FEM to cast what's an infinite dimensional inference problem as a nonlinear filtering problem, and we applied the extended Kalman filter to compute this posterior distribution. To scale it, we used this low rank approximation, and we tested it on some canonical PDEs. So I talked about KDV and Kurumoto-Sivashinsky. The Burger's equation, which is sort of seen as a toy example of the Navier-Stokes equation in 1D, we've tested it on that, and some canonical reaction diffusion systems, which I've spoken about. So just a couple sort of prime examples of extensions and applications. So there's current joint work that I'm doing with Alex, who's also visiting from Cambridge, sitting up the back. And Alex has been working on dynamic variational autoencoders, which are sorts of models that you would use when you're not necessarily sure what this observation operator is, and you want to try and learn what this observation operator is. And also, if you have a strange data set, for example, you're observing images and you want to extract and solve this inverse problem that I was talking about at the start. Maybe you want to extract what those parameters are given a set of images of this flow that you're studying. And then finally, some work that I'm the lead author on, and I want to say that Alex is definitely the lead author on that, is StatFEM for oscillatory shallow water flows, and that's looking at extending these sorts of methodologies towards oscillatory island wake problems that Paul Branson has collected data on, and we want to try and apply these sorts of methods to shallow water problems because it's sort of a logical next step from these relatively quasi-linear PDEs to something a bit more non-linear that is actually a fluid flow. So thank you for your time, and here are some references to this work. Cheers.
Open up for any questions. Must be something. I'm looking at Ed. He's always got a question.
It's something that you taught me when we first met. It's related to the.
Sorry, the question was just if you could expand upon the construction of the I norm.
The I norm is just you just look at it, and if it looks like it's doing something sensible, you know it's okay. Yeah. Yeah.
Just a silly question because I thought no one was going to ask. So, so my question is regarding your finite element part. So how did you actually, for example, what sort of interpolation functions you use there? What is the effect of any errors you get there on the final results and things like that?
So for the FEM component, we just use P1 elements basically for all these examples. So the shallow water stuff uses higher order elements for the velocity field, but all these examples are just P1 linear elements. In terms of convergence rates, what some colleagues in the UK have looked at is when what do the errors look like versus of the Gaussian process. So just in brief, what they've looked at is what does the probability distribution, this thing look like when you discretize it with finite elements versus what it looks like when you don't. So it's the true analytical version that they've looked at and checking how this probability measure itself converges as you refine the mesh compared to its discretized counterpart, essentially. They haven't looked at it for this example. They've looked at it for the 2D Poisson equation or arbitrary dimension Poisson equation. But that's the sort of stuff. And I think they accord with the convergence results that you would get when you look at the Poisson equation is it converging to the true solution? It's order h squared or h to the polynomial plus 1. Yeah. Yep. Yep. Mm. Yeah. Yeah, of course. So the question is it like you have an error in here and these concentrations are bounded from above essentially to be positive? Yeah, the U itself is positive, correct? Yeah. So we essentially just didn't really worry about that. We used a truncation thing that said as soon as it hit below 0, you would just set it above some threshold value and just set it to make sure it is above 0 on the numerical side. We didn't run into any problems when specifying the Gaussian process that it should actually be bounded above 0, because in general, the probability that you will be observing, given the forcing that we were choosing, negative values was vanishingly small. So it wasn't really worth adding the extra component of truncating it at 0, practically speaking. To keep that in a valid theoretical framework, you could look at like a truncated Gaussian process and just have it 0, bounded from below by 0 or something like that. And, you know, if you were sampling from it, you just use a rejection sampler and kill all the entries that have negative entries. But that's a really valid thing to say. I think perhaps there will be some systems where some sort of truncation like that is required, but we haven't really seen that in practice.
Scott? So you said you looked at the Burgers equation.
Yeah.
Did you use an FEM model for that, or would you use a finite volume method? And would it matter if you changed the numerical method you were using to solve the equation?
In general, I think the framework should work across discretizations and should be discretization. I think we stuck with finite elements coherence throughout the work, essentially. We haven't looked at actually applying finite volumes with it. We've looked into like spectral methods and so on because I think there's nice properties about projecting Gaussian process onto spectral basis. But I think the method would work with finite volumes. I think it would just require a little bit of careful discretization of the Gaussian process. But I think it would be okay.
Thanks, Connor. I think we might wrap up. So join me in thanking Connor for the talk. I think we'll call it there. John and Connor, I guess, are around as well for questions. I think by virtue of the fact that they're involved in TIDE, we're going to see them here as visitors during the program. So next year, when we look forward to both Connor and John coming back. So yeah, thanks for coming on, giving the talk, and thanks for everyone online for joining. And yeah, enjoy the rest of our day.